now be presenting my Physics 2212 lab involving magnetic braking with Faraday's law. Faraday's law relates time-varying magnetic field to a Curly electric field whose path integral around a closed path is not zero, but provides an EMF that can drive a current. This current produces a magnetic field, which exerts a force on the source of the external magnetic field. So in this lab, the source of the external magnetic field is the falling bar magnet, and the induced current is driven in a tube of the aluminum foil. The interaction between the magnet and the aluminum foil produces an interesting result, which we will show here soon. So in this lab, I had to collect observational data of a magnet falling through a tube of aluminum foil. I had to model the magnet and the tube interaction computationally, and then I had to compare the computation predictions with my observed data. So the materials I needed were a smartphone, a bar magnet, aluminum foil, and a tape measure. So first I had to find the north end of the magnet using the magnetometer, and I did this by dragging my phone across both ends of the magnet, and when the Z component of the magnetic field was decreasing, that's how I knew I was headed towards the north end of the magnet. As you can see in the video, the procedure involves me dropping the magnet through the tube of aluminum foil, and I recorded the time it took by the time it entered to the time it exited the tube. I repeated this 5 times and came up with a time of about 0.5 seconds from entry to exit. My computational models, the first thing I had to do was set all the initial conditions. So you see the constants that were given, and then I measured my tube of aluminum foil by length, width, inner radius, and then the full radius was calculated. As you can see, the mass of my bar magnet was about 0.023 kilograms, and then the magnetic dipole moment was taken from lab 2. Then I had to calculate the magnetic fields, which I also used from lab 2. Next, I had to calculate the rate of change of magnetic flux. The pre-lecture video 43 completely walked me through this process using some of the same values from lab 2 when it included like r hat was my distance and everything like that. Next, I had to calculate the current, which is not pictured, but I did do that, which is the EMF divided by the R. Then I had to calculate the magnetic force on the magnet by the tube of the foil. And I did this by defining that function, as you can see, taking from the pre-lecture video a lot of the formulas. Then I used Newton's third law to find the magnetic force on the tube of foil by the magnet, which is the exact same thing because Newton's third law is the same magnitude but opposite sign when the force is backwards. Next, I had to calculate the net force by adding the magnetic forces together with the F grav. And then finally, I used Newton's second law to update the velocity and positions of the falling magnet. Here are the graphical models. Each color represents the intensity of a current induced around the foil, each having a different direction. Blue would be clockwise and red is counterclockwise. The dynamics of the system are the exact same if the bar magnet had been flipped around, and we actually worked out an example like this during lecture. The shape of this velocity versus time graph tells me that at the time where the velocity is constant, the straight line, all of the forces acting on the bar magnet cancel out and equal 0. So what if the resistivity of the conductor were reduced as close as possible to 0, and how would that change things? Since there would be no resistance, eddy currents would not decay and would form perfectly to oppose any changes in magnetic flux. There would also be complete magnetic flux exclusion due to the absence of magnetic fields. So overall, the magnet would levitate or fall extremely slow. So what if holes or slots were cut into the tube? How would this affect the ring currents? This would disrupt the formation of the eddy currents, which are things that cause the braking to slow down the fall of the magnet. The induced currents would also become weaker and limited to smaller loops. there would be less magnetic opposition, which would equal less braking force. So overall, the more cuts or slots, the less effective the eddy current braking system becomes. Thank you.